Sí, sin problema. Pero creo que es más fácil. Salta la granja porque no hay tanta competencia en general. Y tiene que estar como muy curtido, muy batallar mucho para conseguir.
Alrighty, we can find our seats.
En ground es tan difícil comparado con.
Hello.
Yo creo que sí.
Alrighty, welcome to our afternoon session, Interdisciplinary Aspects. I'm Patrick, I'm your chair for this session. And we're going to start out with a talk regarding stellar flares, M-stars, and its rocky planets.
Okay, thank you. Hello, can you hear me? Well, in the mic? Okay, I can hear myself. Okay. Well, hello everyone. Nice to meet you all. My name is Laura Amaral. I'm a postdoc at ASU. I'm working with Virginia. And today I'm gonna talk to you the role of flares from early and late M-stars in atmospheric escape of rocky planets regarding the hydrogen escape. So we have seen before several times the flat curves from JWST from rocky planets around M-stars, and something that we always, the community is wondering about it is why that happened, why you're not seeing any atmospheres in those planets, and if that might be driving by something like stellar activity, because in the case of M-stars, they are very active. So to answer this question, like, are stellar flares important for atmospheric escape? I'm gonna show you here my work. So right here, what you can see is a flare, just like a example from a super flare from Proxima Centauri. And what you can see here is basically that stellar flares and M-stars, they are very frequent comparing to the sun, for example. So in the meantime, the super flares in the sun happens twice per cycle, like each 11 years, we have 1 or 2 super flares. For M-stars, you're gonna have those type of flares more or less once per day. And that's a lot of, like, can be a lot of XUV and radiation, like as an input for the planets, and that might be driving escape. So to figure out this problem, what we did, we built flare frequency distributions. That is basically those type of diagrams. Here you have like the flare energy, and you have like how often this flare have happened for day, his log day. So we did that using M-stars, late M's and early M's as example. So in this case, here I have like late M's for like young clusters from like 15 to 7 million years, and field age. And in this case, this is like adaptation from Lloyd 2018 from the HAZMAT program. That's basically showing how the flare is changing also over time. So you can see it is basically for early M stars, you have like this change on the flare frequency. It's kind of has like a jump for field age stars. Like field age stars, like more than 1 giga year old. And while for late M's, basically we have about the same activity they have for like early, but all over like regardless the age. So like it doesn't change too much. So basically the same activity over time. What I did was I made a model to see how like to fit this change on age to basically understand how much XUV from the flares gonna arrive in the planet, plus the quiescent emission of the star that also emitting like XUV. So I put that in my code that I'm developing, is the vPlanet code, and basically understand how it gonna affect. So I consider radiation recombination escape and energy limited, and that's all for the hydrogen. So for now, no secondary atmospheres, but I'm gonna contextualize that next. So basically, the first example that I have here is for TRAPPIST-1. So basically, here we can have, it is like the XUV flux arriving in the top of the atmosphere of the planet, and here's the hydrogen envelope mass changing over age. And okay, and the solid lines, it's when you don't consider flares, just quiescent evolution, and dashed lines when you add the extra XUV from flares. So basically, this is TRAPPIST-1b, is the closest planet from TRAPPIST-1 star that is like a late M. And if you can see here, basically, flares don't add too much for the evolution. Basically, you just accelerate that in like 4 million years, more or less. But this is the case for closing planets. So if I just add another planets here, consider that like TRAPPIST-E and F are in the habitable zone too. So basically you see like all the planets that are closing, they don't have like that much of difference for like the escape. And while the ones that are like a little bit farther, like TRAPPIST-1F, basically start to change, like accelerate the escape rate, accelerate the escape a little bit. Like in this case, gonna be a couple of like 100 years. When you move farther, like for TRAPPIST-1H, for example, that is like in the other side, other side of the habitable zone. Basically what happens is you're still losing all the atmosphere, but for the case of TRAPPIST-1H, what happens is this planet is too small, so the gravity, it's not that high, so basically they cannot like keep the atmosphere anyways, and the flares isn't going to accelerate the process too much because the quiescent going to be enough to drive the escape. But if we move to planets like planet TRAPPIST-1F or G, like I told you before, basically that is like in the habitable zone or a little bit farther, they have more gravity, and what happens is they can keep the atmosphere for longer, but if you add the extra XUV from flares, you're actually accelerating the process of total atmospheric loss and about like 2.5 billion years earlier. So basically, like that's when flare is gonna matter for the evolution of the system. If we move for early type M's, what happens in this case, we have AUMIC here, and I took AUMIC-D as an example. AUMIC-D is an Earth-sized planet. So what I did is I put AUMIC-D in different positions from the star. So in pink, we have the AUMIC-D in the current position that is very close into the star. Then the brown one, it's when it's like at one astronomical unit equivalent, like the Earth from the sun, from the star. And that means that it is in the habitable zone. And the AUMIC-D here, like in orange, is basically when it's in the outer habitable zone limit edge. So there's 3 different cases. Like one is too close into the star, one is too far away, and one is just like in the habitable zone. So close in, again, flares doesn't add too much. The quiescent is sufficient to drive the escape. When you move that to the habitable zone, basically you accelerate the escape in like 1.6 giga-years. And when you move a little bit farther, basically even if you add flares, the atmosphere is gonna be still there. So just to be like in the state of the art, what I add here was the cosmic shoreline, adding flares. So basically what I did is just like I integrate all the flux of the the star, considering flares over time for all those planets. Those planets are from DDT program. There's not all the planets here, just the couple like around late M's and early M's. So basically some planets, what happened here, like TOI 700D and another TOI like 198B, they're gonna kind of cross the cosmic shoreline, basically. So what this plot shows to you is that flares will make a difference, like the flux from the flare is going to make a difference over time, over the evolution of the star, but not too much for planets that are like close in, basically. So also tomorrow we're going to have Emily Pass talk that is very the same context of like about flares and cosmic shorelines, so take a look for that. And yeah, so here are like basically the results overall. So stellar flares will accelerate the total atmospheric loss by a variable amount, depending how like the time that you're looking for the star, like the age of the star, but also the distance from the star. So we should be looking for flares like, for planets that are in the habitable zone of those stars. If you want to see the impact of flares, if you want to keep the atmosphere, you should look for planets that are like on the outer like limit or beyond. So the flares will dominate basically the XUV emission like for like old stars, like after the saturation phase. That's when it will start to drop like the quiescent emission. So what that means is if you consider, for example, when the Earth secondary atmosphere started to build up like 3 billion years ago, so the sun will have like 1,000 years or like a billion years or something. Basically, that's when like the secondary atmosphere in the Earth started. That's basically match when the flare is going to start to make a difference. That means that is for secondary atmospheres observed like now for JWST or any other like telescope, that's when you should be caring about the flares. So in this case, the flares will matter for secondary atmospheres. I don't have the results yet. This results is just for like hydrogen, like primordial atmospheres, but we should take that into consideration, especially for planets that are in the habitable zone. And yeah, like I said before, that atmospheric rotation will be more like likely possible if we're looking for the planets that are like in the outer edge of the habitable zone or beyond. So I'm gonna leave this plot here. So basically, it's like a overall idea, like a schema what I'm talking about for you. So basically, the quiescent emission is going to be sufficient to deplete the atmosphere when you're too close enough the star. If you're too far away, the Earth-sized planets are going to be able to keep some atmosphere. If you're in the midway, like in the habitable zone, basically flare is going to be necessary if you want to deplete the atmosphere. So here is the last paper that we published this year if you want to take a look. And I will take any questions from here. Thank you very much.
Questions? Yeah, really interesting talk, Will Meisner from Carnegie Science. I was wondering if you kind of have a ballpark for when, like what sort of stellar mass this starts to be important. I know you kind of said early versus late M-dwarfs, but you just like, so if I look at a planet, a system, I can be like, what is this planet?
Yeah, that's a good question because like since the escape rate's gonna change for like the FFG is gonna be different for each like spectral type, right? How are we gonna change? So for now, what I have the results is like just for early M's and late M's. So in this case, I'm consider is like a late M's that are like under like 0.11 solar masses. And for the early M's is like very, very early, like AUMIC. I would say that, let me show you the last one again. So I would say that that limit that I'm showing, oh no. Oh my gosh, okay. You can put that in the bingo card that I put in the wrong slide. So basically what gonna happen is this like boundary gonna change. So if you have less flares, what is gonna happen is this boundary gonna move towards the star. Also, they have to take in consideration the gravity of the planet. If you have like a more massive planet, you're gonna keep the atmosphere for longer. So basically, it depends. So like always, but likely FGK star is gonna have like a lower flare rate when they're older. So I'm gonna say that this boundary is like close in. But if you have a high flare rate, you have to push this boundary like farther. So it's not too much like about like the spectral type, I would say, because some stars just like have like a higher frequency, flare frequency distribution, even if you're like I don't know, or older or like another spectral type. So you should focus on like the flare rate more than like the spectral type, I would say. Yeah, I hope that answered your question.
And quickly, there was a question online from James Owen. Thanks for this nice talk. In your mass loss modeling, you assume that the mass loss rate responds straight away to the flare and using the flare energy with the same mass loss efficiency as the quiescent state? ?
Oh, okay. So what I do, it is, sorry, I have a lot of extra slides. No. This one, yeah. So depends on the flux. So what the code does, it is we jump from like radiation recombination from energy limited depending on the flux. So if the flux is too high, gonna be radiation recombination. If it's too more like lower, gonna be energy limited. It's like two extremes from like the hydrogen dynamic escape. The hydrodynamic escape. But yeah, I don't do like flares like a pulse. I just average out the luminosity from that. So what I do it is I calculate the flare frequency distribution over time. I calculate how much luminosity those flares gonna produce, and I'm gonna start to put like data points in my model and see how that evolves over time. That's basically what you're seeing here. So here's like with flares. So just like adding this extra XUV to the quiescent emission. But it's an average out. It's not. I'm not doing like individual flares. That answer your question? Oh yeah, sorry.
Perhaps.
I hope so.
James says yes.
Okay, thank you.
All right, we should move on to the next talk, but as always, use Slack for questions.
Thank you.
Oh, okay. So hi everyone, I'm Emma. I'm a third year PhD student working at the University of Groningen in the Netherlands. I'm working with Tim Lichtenberg. He has one postdoc position and one PhD position open right now, so if you want to join the Forming Worlds group, that's the time. And today I will talk to you about atmospheric evolution and escape on molten super Earths. So a bit of introduction about rocky exoplanet population. So out of all of the confirmed exoplanets today, 1/3 of them are believed to are classified as super Earth and terrestrial planets, and some of them are presented here in this mass radius diagram. And the one I'm interested in are the ones that are colored in red. So all the planets here are colored by their equilibrium temperature. And the red points here suggest that they are in a molten stage, so in a global magma ocean stage. And for a planet to be in a magma ocean state, there is different evolutionary pathways. So the planet can be in a bare rock, meaning there is no atmosphere, it's molten on the day side, but the planet can also retain an atmosphere and be in a magma ocean stage because it's in a runaway greenhouse state. And during this magma ocean phase, there is a lot of interaction between the atmosphere and the mantle, and that's what is shown here on this scheme. So here you have a scheme of the structure of a magma ocean planet, and you can see that here in the mantle, you have a lot of volatiles that are dissolved, and when the magma ocean solidifies from bottom up to the top, all the volatiles that are trapped inside of the mantle are being outgassed in the atmosphere. So when we model the evolution of magma ocean planet, it's important to understand the feedback between the atmosphere and the interior, and that's what I want to stress here. Another thing which is important is atmospheric escape. First, I wanted to show the evolutionary figure, like the clock figure, but Laura already showed it in the workshop, so thank you. And instead, I was thinking, okay, I will just present to you like an artistic view of magma ocean planet undergoing strong atmospheric escape. And the point I want to make here is that the timescale of the mantle crystallization happened at the same time as atmospheric escape. So this is something important to take into account when modeling magma ocean planets evolution. And with all of that in mind, I was trying to understand how does the composition of the secondary atmosphere arise on those very irradiated exoplanets. And for this, I'm using the Proteus code that we use in my group. So Proteus is a coupled atmosphere interior framework that we use to simulate the evolution of rocky planets. And here you have a scheme on how this works. So Proteus is a framework that works with a lot of different modules. And here I only display the modules that I use in my simulation. There is many more modules that are available to include much more physics and chemistry, and everything is available open source on GitHub, so you can go and check it out. But if I focus on the module that I use in my simulation, so I use the spider module that compute all the evolution and of the interior dynamics of the magma ocean planet. Then we have some interaction between the atmosphere and the interior, which is done here at the surface with the different ingassing and outgassing of the volatile species that we have in the code. Then I use two different treatments of the atmosphere, one which is fully convective and another one which includes a convective shutdown. So this allows for a radiative layer within the atmosphere. Then at the top of the atmosphere, atmospheric escape. And we have an energy limited formalism for this now. And then stellar evolution for the evolution of the XUV flux to compute the escape. So this is how this works. And so I ran a bunch of models, and the first thing I wanted to look at is the influence of atmospheric escape on the magma ocean solidification timescale. And that's what I'm showing here. So here you have two panels. The x-axis shows the evolution in time. Top panel here shows the evolution of the surface volatile partial pressure. And here, this is the mantle evolution over time. And the main difference here is that I ran two simulations, one that include atmospheric escape here with energy limited formalism with the solid line, and one without energy limited escape with the dashed line. So if you focus on the results here, when I look at the simulation without escape, my planet stays in a steady state, and there is still an atmosphere on this planet, and it's still in a magma ocean stage. But when I include escape, as you can see here, all the atmosphere is lost, and then the mantle solidifies quite quickly in less than a few mega years. So in that sense, atmospheric escape can accelerate the magma ocean solidification timescale. So that was the first thing I looked at. And then I was thinking of investigating the impact of different treatment of the atmosphere, and that's what I'm showing here. Here you have a PT profile of the same simulation with different atmospheric treatment. So here I use either a convective atmosphere, and that's what you can see here with the dashed line, or a radiative convective atmosphere that correspond to the solid lines. And I show the evolution in time of the planet I'm simulating. And if you focus first on the convective treatment of the atmosphere, you see that it doesn't really evolve in time because my planet stays in a steady state. And here I end up with a CO2-dominated atmosphere, and the planet is still in a magma ocean stage. But when we include radiative convective treatment of the atmosphere, you can see that the planet cools down in time. And this leads to the mantle solidification within 0.1 gigayears. And once the mantle solidifies, all the water that was contained within the mantle is being outgassed. And that's why I'm ending up with a H2-dominated atmosphere. So that was for the comparison between two different simulations. And after this, I wanted to investigate a wide parameter space, and that's what I did here. So I ran a 2000 simulation varying the initial volatile budget, the semi-major axis of the planet in the system, the stellar type also. And I wanted to see if I could see some trends in this exploration of the parameter space. So what I'm showing here is a cumulative distribution of the final mean molecular weight of the simulated atmosphere at the end of the simulation. And I show this for 3 different redox states of the mantle. So this is a measure of the geochemistry of the mantle. And I show this here for like a very reduced mantle with the blue lines. So this means you have a lot of hydrogen in your planet, and a very oxidized case here, meaning that you have a lot of oxygen in your mantle. And what you can see here, looking at this distribution, is that if you start with a very reduced mantle, you end up with very light mean molecular weight atmosphere and mostly H2 dominated. But if you start with a very oxidized mantle, you end up with very heavy mean molecular weight atmosphere, CO2 or SO2 dominated. So that was the first thing I looked at, and this has been shown already in the previous talk during this workshop. And once I saw this, the influence of the mantle redox states on the resulting composition of the secondary atmosphere, I wanted to see if the other parameter that I tested in my grid had an influence on the composition of the secondary atmosphere. And that's what I'm showing here. So here I'm showing again on the y-axis the mantle redox states of the planet. And on the first panel here, I'm showing different values of C2H ratio at the beginning of the simulation, and also different semi-major axes for the generated planet. And then you can see all of the bubbles are colored by the final mean molecular weight at the end of the simulation. And the first thing you can see here is that the color gradient is much stronger on the y-axis than on the x-axis, because you go from blue to yellowish, let's say. So in that sense, the interior geochemistry dominates over the carbon budget or the orbital distance of the planet when looking at the composition of secondary atmosphere. And I wanted to look into different regime when I was looking at all of the generated planets, and I was looking first at the very closing orbiting planet that are that start with a very oxidized mantle with a very high C2H ratio, and I see that for those planets I end up with mostly high mean molecular weight atmosphere that are H2S dominated or CO2 dominated. Then for all of the planets here that start with a very neutral, let's say, redox state, I end up with a water-dominated atmosphere. And finally, when I look at the planet that start in a very reduced state, that are orbiting closing the aster, I end up either with a hydrogen-dominated atmosphere or CO2-dominated atmosphere. So those like red dots here. So I thought that this was really interesting. And with this, I hope I convinced you that the magma ocean solidification timescale, as well as the escape together, strongly influenced the secondary atmosphere of rocky planet during the evolution and evolutionary timescale. And when I look at the composition of this secondary atmosphere, they are strongly shaped by the interior geochemistry of the planet. And I end up with like a wide variety for the composition of those secondary atmosphere that range from H2 dominated atmosphere up to CO2 dominated, SO2 dominated atmosphere. And most of the simulated planets in my simulation end up water dominated. Thank you.
Questions for our speaker?
First of all, awesome talk. You mentioned on slide 11 that redox state, initial redox state is the main control for final atmospheric composition. I was kind of wondering if maybe there's some connection to that and orbit distance. Like, I'm not a formation chemistry person, but do redox states, like initial redox states, depend on anyway and formation distance from the host star?
Good question. For the planet I simulated here, I was just randomly choosing like the redox state. I was testing like these 3 values for like all the orbital distance. To be honest, I'm not so sure, so I don't want to say something wrong. If someone knows, please let me know. But yeah, that would be something to investigate when I model those planets to be sure that, I don't know, if a planet starts more radius when it's closer to the host star, I take that into account. Yeah.
Quick question.
That was actually my question. It is an amazing question. You asked it far better than I could. When you're doing energy limited atmospheric escape, are you just assuming that like basically all of the atmosphere is going with it? Is it launching at a certain point, or are you just removing atmosphere over time?
Mm-hmm. So I remove the atmosphere during the whole evolution of the planet during the simulation. And what we do is that we take only the species that are being outgassed from the mantle. And then, for instance, you have like a CO2-dominated atmosphere. I escape only the atomic, the atoms from this species. And yeah, about RxUV, so where I put RxUV, so where I start my atmospheric escape, I tested different values in this grid, and I didn't see much difference, which was a bit intriguing for me. And then I had a nice discussion at this workshop with some people that told me how I could implement like in a better way how I compute RxUV, because for now I was just randomly choosing a value in my atmosphere. So
Let's thank Emma again. We'll now welcome Li Zhen talking about Uranus as an exoplanet. Take it away.
Hello, friends. I'm Li Zhen Chen. I'm here as a private citizen to explore a few possibilities driven by coronal mass ejection. Thank you to the organizers for empowering me to be here. So, Uranus is in the far perimeter of our solar system's backyard. And the emissions in UV especially, or in UV or in X-ray, are typically weak or inconclusive. That's why we want to bang the planet with CMEs. That would increase the emission strength by orders of magnitude. Here are examples taken from real data, our sun's coronagraph, and propagate the CMEs out all the way to the Uranus orbit right here. And these are taken from about 3 months worth of data, including the Mother Day's storm, if you remember the bright aurora display all the way south to Mexico. Okay. The quantity shown is pressure, and if we just take one entire ecliptic plane, and that will be here, and that's just one-time snapshot. This is the radial velocity, and here's Uranus again. And then if you take profile, this is the whole about 3 months worth of time. You can see radial velocity, density, pressure, magnetic field strength, and know that there are these time periods when the enhancement is really orders of magnitude stronger. Okay, so take a look at, and you can pick your favorite active star, and just imagine that it keeps firing CMEs outward. That's the Mother Day storm. Earth is right here. And you see these CMEs run on top of each other. They are the strongest. They represent the strongest disturbance at the faraway planet. in CMEs, high charge state heavy ions will be enhanced. Their abundance is enhanced. And these high charge state ions, they interact with exosphere, the geocorona, like what Dr. John Clark had discussed with us. So what we do here is to really take the data and model this model-day storm, like for Earth, and then scale it to Uranus to estimate what kind of soft X-ray we see. Because when those interact, when the heavy high charge state ions interact with H atom, hydrogen atom, they give out soft X-rays. So we start from really close to the planet, only 30 planet radii away. And to see Uranus, you are always, because we're earthbound, like Hubble, JWST, we're all like earthbound and we're on the sun side. So we're looking at Uranus's day side. So that's why we're looking at from the day side, and you will see this, wow, strongest emission. Those are the cusp, the funnel-like structure because of the magnetosphere interacting with the IMF. And you zoom out to 60 and 220. This is to, like, imagine if we put a camera on the moon, and this is a camera at the L1. So the end result is that we can have detectable signature that for CRISM observatory. So CRISM is like really good at spectral resolution, and it can accumulate, over a long time. So this will take a few tens of hours only that you can get the soft X-ray emission. If we can combine with Chandra has nice spatial resolution, then we really can see the interaction due to stellar wind, our star interaction with the exosphere. So here now, let's take our imagination like far outside of our solar system. But we start from close in. So these are different perspectives. If we were looking at the stellar system with a star here and the planet here, that's a side view, like the transit kind of picture. That would be this kind of perspective. And we just zoom ourselves way, way out for tens or hundreds of light years. And for this one, it's the head-on view. You're looking down at the orbital plane of the planet. And whether we will see distinct features, that's our next step. Right now, here we are just too close to see much difference. The outstanding difference between these two perspectives is the cusp, these almost horizontal regions, and those are the islet that you see in the previous image. All right. If we have a mission that can image Earth's magnetosphere at around 30 Earth radii away from the planet, we can see blinking eyes. Like it will need to be right between the sun and Earth, along that line, looking at Earth about 30 RE away. That is when the interplanetary magnetic field is southward during the CME. And if it turns northward, it's going to widen up. And that you can see from this side view that I'm going to play for you, this movie. This is within that model day storm. when like strong solar wind density pulses keep bombarding our magnetosphere. That's when the IMF is almost south. See how that, wow, the Earth is just, wow. All right. Now that's, like, look at the outflow, ion outflow. So I'd like us to first focus on this cartoon. This is for Earth. And you know, during CME-driven storms, like Earth origin ions, for example, O+, they will come out of this cusp region. This is what I call cusp region, the funnel shape region. They will come out, just one example, in the hollow wind solar storm in 2003, O+ ions were observed, like energized to tens of keV at 9 Earth radii altitude. They can go that far. So imagine you look at Earth from the sun side again, like Sun-Earth line, and you will see, what will you see? You will see these fountains of ions, O+ ions. And that's not the end of their journey. They go to the night side because of the solar wind blowing all these field lines to the night side. And when the magnetotail reconnection, like Shannon discussed, when that occurred, these escaping O+ actually can be brought home. These reconnection will take the O+ ions back closer to our planet, forms a ring current, energetic ring current. Really during storm time, O+ ions, dominant ion species for ring current. So if we image that, you will see kind of a ring, Earth, planet, and then a big ring of O+ ions around it. So that's for Earth. Now for Uranus, these are data, real data from JWST, Kersey, Henrik. So what you observe aurora spots. These are possibly related to that pair of cusp. And if you tune down this color scale, you begin to see non-auroral emission. And if you tune it down further, just around this southern spot, you see this emission extending outside of the planet disk. That is H3+ outflow going away from the planet. So here's one possibility. We can have joint JWST and Hubble observation with Hubble having this 52 × 2 arc second slit. I really can image the exosphere and the outflow as well. Occasionally, CME can create highly unusual condition. Like for this case, it takes our planet inside the Alfvén surface. Usually the Alfvén surface for our sun is like only a few tenths of solar radii from the sun. But for sometimes that can happen during CME. It can punch a hole of that surface and displace that all the way out to 1 AU where we are. Typically during CME-driven storm, that's the auroral emission pattern you will see. It's pretty global. Take up important fraction of our planet disk. However, during the subalfvenic solar wind, when Earth has this off-end wings connected back to the sun, the emission is very different. Look at it. This is observation. Thin arc on the day side. And the night side is not as intense, but it's diffuse. So that's what making baby steps to simulate this physics. Well, please explore with me these possibilities. Take it outside of our galaxies.
Any quick questions for our speaker?
Nice talk. Okay, I have a crazy question idea. There's any infrared detector that we could look into Uranus transiting the sun and try to detect the helium?
So that will have to be outside of the Uranus orbit so that you can see Uranus doing the transit. Right now we don't have it, but that's such a great idea.
Okay.
Any other quick questions?
Outer Worlds mission. Hi.
Hi.
I was wondering, so the last decade of auroral observations on Uranus and Neptune, has they yielded tighter constraints on the magnetic field moments over what we had with Voyager? I know that was an idea once.
That is, I think so. I think Lamy?
Yeah.
Yeah, I think they're working on that.
Okay, right.
Yeah, it might have already results.
All right, let's thank our speaker again. Did you turn the microphone on?
How do I do that?
It's just a little.
It's green. Oh, I can hear myself a little bit. Oh, that's wicked.
All right, now we welcome our speaker, Abby, who will be talking about active volcanism on terrestrial exoplanets.
All right, can everyone hear me? Cool, and there's the clicker. All right, so hi, I'm Abby Boehm. I'm a fourth-year PhD candidate at Cornell University. And what I'm going to present today is something that I've been working on with my advisor, Nicole Lewis, as well as our collaborator, Daryl Seligman. It's effectively just a really roundabout way of characterizing volcanism on terrestrial exoplanets. So at this atmospheric escape and replenishment workshop, I think we all harbor hope that we will find systems where escape and replenishment are balanced, and that will allow an atmosphere to persist as long as the volcanism keeps on going. But there's not always a guarantee that volcanism is going to result in an atmosphere, even if the volcanism is still ongoing. If you're in a system where atmospheric escape is just that efficient, it will outpace volcanic outgassing for realistic outgassing rates of which we're familiar with, like solar system level outgassing. And so you wind up with these worlds that are airless despite their active volcanism. Poster child of this issue is probably Io in our own solar system. It has an exceptional volcanic output and yet less than a millibars worth of atmosphere to show for it. So inspired by the plight that Io is in, we wanted to look to Io for some inspiration as to how we could find volcanism even on worlds that aren't capable of maintaining atmospheres. And the way this works is going to require a little bit of a history lesson on Io itself. So famously, volcanism on Io was more or less confirmed whenever we imaged its volcanic plumes directly with Voyager. But prior to those images, there was still evidence of Io's volcanic activity. It just hadn't been correctly interpreted until the context of the Voyager images was available. This evidence was the fact that radio and optical emissions proved that Io's orbit path was filled with ions. And the original source of those ions was attributed to sputtering off of the surface. But once the volcanic plumes were imaged, the volcanic connection was made clear as follows. So first of all, we have Io. It has its volcanoes. They go boom. And they outgas some volatiles. Primarily, this is going to be molecular sulfur dioxide. Then these volatiles are subjected to bombardment by all the energetic particles trapped in Jupiter's radiation belt. So these particles come in, they dissociate the molecules, they break them apart and ionize them, and that yields a nice cloud of sulfur and oxygen ions. These are relatively lightweight, so they escape very readily, where they are then intercepted by Jupiter's very powerful magnetic field. Now, this plasma cloud is rarefied and highly conductive, which means it is subject to magnetic confinement by the magnetic field, which basically means that this magnetic field is going to lock onto that cloud and force it to move alongside the magnetosphere. Jupiter's magnetosphere rotates much faster than Io's orbit period. It's roughly 10 hours as opposed to 42 hours for Io's orbit. And so what's going to happen is that these ions are going to be dragged away from Io and spread out all throughout its orbit path, slowly building up a big circumplanetary torus of plasma entirely supplied by Io's ongoing volcanism. Crucially, this confinement process is not perfect. Gory math I won't go into too much here, but the key takeaway is that once the plasma is injected at Io's orbit distance a, it will slowly drift radially outwards over a timescale tau defined there, which is estimated for reasons of the math was not quite complete at the time. But it will drift radially outwards until it hits Jupiter's Alphean radius r sub a. At that distance, the solar wind is going to overpower the magnetosphere and the ions are going to get whisked away. This timescale for Io is roughly 20 to 80 days, which means if you turned off Io's volcanism, the entire plasma torus would be dispersed within that timescale. So not only is this torus proving that volcanism is ongoing, it's giving us a timescale for the volcanic outgassing process, and it's giving us an estimate for the volcanic outgassing mass supply rate. So that's a lot of insight to gain into something that doesn't actually require a permanent atmosphere to exist. And so inspired by that example, we basically asked this question. If you can stick an outgassing moon into a planetary magnetosphere and have it build a torus, could you do the same by jamming a planet into a stellar magnetosphere? Obvious first concern, stars are not planets, brown dwarfs notwithstanding. I'm not going to touch on brown dwarfs right now. But there are a lot of processes that happen inside of stellar magnetospheres that are to be concerned for torus formation that are not concerned in planetary magnetospheres, things like flares and the source of the radiation being much, much bigger than the Kelvin-Helmholtz contraction radiation that Jupiter gives off. Despite these concerns, we do at least have this empirical evidence. There is an ultra-cold dwarf star, M8 spectral type, which has, through radio emissions, been confirmed to have radiation belts indicating it has magnetically confined plasma in its field, analogous to Jupiter's radiation belts. So we can at least say that for the absolute smallest of stars, this physics does scale up. I will assume that there is some upper limit of stellar type where this is going to break down. For now, I will press ahead optimistically with the belief that GKM stars will suffice. But this is definitely an area of further work that should be done to make sure that that is not too optimistic of a statement. Assuming that these stars can maintain plasma tori, how would we actually know that they are there? If we restrict our attention to transiting exoplanetary systems, where the stellar rotation axis and the planet orbit vector are more or less aligned, then the torus that the planet's volcanism builds will follow its orbit path. And so just as the planet occults the star, the torus is also going to occult the star. Crucially, this occultation is going to be perpetual because it's filling out the entire orbit path. So rather than seeing an intermittent transit signal, you're just going to wind up with this sort of chronic, like persistent contaminating absorption features showing up in the stellar spectrum that otherwise should not be there. These contaminating features will reveal both the presence of the torus as well as the composition of the outgassed material. We can take this one step further and tie it back to the mass injection rate using some of that math that I sort of sped past a bit earlier. Basically, if your planet is outgassing slowly relative to the timescale tau, the resulting quasi-steady mass of the torus that is going to be built will be small. And with the amount of material occulting the star being small, the absorption features will show a shallow depth. Conversely, rapid outgassing should build a large torus with deep features. So overall, if this structure does exist and can be detected, it will be a way to confirm the recency of the outgassing, the mass injection rate, and the composition of the supplied material. This would be a really big amount of insight to gain in the absence of both atmosphere and resolved imaging. So the last question we asked for our project was, is there anywhere that we know about where this could actually be done? We basically scoured the archive for some exoplanets that would fit all of our requirements. First of all, it had to be terrestrial radius. No disrespect to gas giants, but I don't think they have volcanoes on them. The next requirement was an orbit within the stellar Alphine radius. Now, as we saw in this morning's talk, the Alphine surface of a star is a very complex and messy structure. For this first pass work, we have simply assumed that the Alphine surface is spherical with a fixed radius, but future work could include accommodating the fact that the Alphine surface is quite a messy structure realistically. General rule of thumb, Alphine radius for a star is usually order of AER star under 10, under 5 if you want to be conservative. Finally, we also limited our search to targets that had a known stellar rotation period. This is necessary so we can estimate the torus lost timescale tau. With all that rolled together, at the time of writing, we came away with 33 exoplanets for which this work could be approachable. We award a little extra priority to anything that's eccentric because eccentricity favors volcanism via tides. And with all that together, up here at the very top, GJ367b stands out as probably the most important target to follow up on. It has a significant timescale of over 100 days, and it would only require an outgassing rate comparable to Earth's, like of magnitude 10 tons per second or so, to generate a torus that would be detectable by Hubble today. So definitely sort of the priority target for us to start checking out and looking for any of those spurious absorption features. All right, just to sort of summarize, if you want to hear about the other 32 targets, or if you'd like to see more of the heinous math that I did not put on the slideshow, it is all in that paper over there. You can check it out. Overall, this method could present a really interesting way for us to probe volcanism even if atmospheres cannot survive, which would be a huge insight for what are usually otherwise regarded as sad flatline outcomes. As an extra takeaway that's not written here that I do want to leave you with anyways, this talk got put into the interdisciplinary aspects section, I think for pretty good reason. We are facing everything from stellar magnetohydrodynamics all the way to planetary geodynamics. Those are all very different fields, and there is a lot of directions that this work could go, like really diving into the rabbit holes of each of those little topics. So if this is a topic that sounds like really interesting to you, and you happen to be an expert in any of those things, I would love to chat with you about where you think this should go and how we can improve it, because there's so much we could do with this, and I would so love some insight. So with that, I'll take questions.
Katie?
Okay. Hi, Megan Wonderman, University of Maryland. Super interesting. I had a question about, so you addressed your scaling up of Jupiter to a star, but I'm curious about the scaling up of Io to a planet, and in particular, whether there would be an influence on the generation of a torus if the planet also had a magnetic dipole, and how that would change the interactions.
Right. So I will say we generally worked doing a sort of scaling up of Io. We're considering an unmagnetized planet because to all indications, it seems like Io does not have an enormous magnetic field to it. I would also be curious as to whether or not the magnetic field of a planet could possibly mess up injection into the stellar magnetosphere. So we did not deal with planetary magnetism, but that would be a really good follow-up to make sure that that doesn't interfere with the plasma entering the stellar magnetosphere correctly.
This is so cool. I was, you said no shame on points, but I was wondering if this might not also be a neat thing to try to detect exoplanets.
So that is already being explored by Apurva Oza and a few others related. Yeah, so there's sort of like two prongs I've seen that this work is getting picked up on. Some of them are let's go straight for the stellar magnetosphere, and others are let's go for a planetary magnetosphere hosting an exomoon. Both have their own challenges, both have their own merits, and both should absolutely be carried forward because they're really interesting.
Hello, Michael Zhang, University of Chicago. For GJ367b, or maybe for some of the other targets, how do the text filters?
Right, so the critical thing would be looking for these absorption features. So GJ367b is transiting, and assuming it is not misaligned, which I don't think we have any evidence to suggest it is, torus that it would build would also be transiting, quote unquote. It would be perpetually in the way of the star. And so it would be impressing these absorption features into the stellar spectrum that shouldn't otherwise be there. Now, there is a small chance that absorption features in a stellar photosphere should be a result of stellar metallicity instead, like metals in the photosphere. I think the biggest giveaway that they're planetary in origin is that they will really selectively enhance only the materials that are being outgassed by the by the source planet. So it's not going to be like a blanket metals contribution to the stellar absorption spectrum. It's going to be very specific elements that are being enhanced substantially over all the others.
Which metals?
Oh, like for which planets?
Yeah, which metals do you expect to be enhanced?
Oh, which metals, right. Depends on, this is going to come back to the redox discussion, what is being outgassed by the planet. And so if you're in a reducing state, if I remember rightly, you're going to have a lot of hydrogen and sulfur enhancement. If you're in an oxidizing state, you will have a lot of carbon and oxygen enhancement. I think my personal take is the ones most favorable will be things outgassing stuff like sulfur, because I can reasonably see oxygen being in a stellar photosphere. Things like sulfur are pretty out of place. That is a really odd one to find in a photosphere.
Quick.
Yeah, just sort of almost a follow-up on that. So you mentioned, right, that we, this might be a way to escape the sad flat lines. But that raises the point that we're looking at a lot of these close and rocky planets with JWST anyways. Do you think there would be any absorption signatures in like the JWST wavelengths we're looking at?
So a lot of them are atomic, which is why I said Hubble, because atomic lines dominantly are in the UV and visible. And so the atomic side of it is really favorable for Hubble work. That being said, I have also thought about could we spin up James Webb stuff to do for this. And while I didn't discuss it here, there is another feature typical of the Io plasma torus called the neutral cloud. Basically, the sulfur dioxide molecules spill out into this cloud first, and then they break down and go into the torus. And so neutral cloud absorption could be accessible by James Webb, while circumstellar torus absorption by atoms would be accessible by Hubble. So really good opportunity for James Webb-Hubble synergy here in those systems.
Alrighty, let's thank Abby and all the other speakers. And by the looks of it, we have a break, and we will return at 3:45.
It's actually one of my second ever talks. So.
Really?
Yeah.
You did fantastic.
We can